Hi everyone. I'm Alex Bradbury. I work at Low Risk CIC, where we work on open source hardware, RISC V designs, and we've been driving the effort to support RISC V in upstream LLVM. So today's talk, I'm going to give I've sort of split it into a few sections. So I'm going to start by giving a little bit of background and some preliminaries, a little bit of insight into what it actually means to port a compiler like LLVM to RISC V. Then I'll talk a bit about how I've gone about the task, some design decisions, and then pick off a few topics which I felt were maybe representative of the sort of design decisions and tasks that we've been taking on in this effort. I'll of course give a bit of a summary of current status and then an idea of where we're heading in the future. Yeah, I can try. So first of all, what is LLVM? LLVM is a popular compiler infrastructure. It has a permissive license, just in the last couple of weeks changed to Apache from a BSD style license. It has a library-based design, which many people find useful. We may integrate it into our projects. And it's often used paired with the Clang language front end, which is the equivalent of GCC in terms of giving C and C++ support. And as we'll touch on later, there's a number of other languages which have used it as their backend, most notably Rust, which I know is one reason why a lot of the distro people are particularly interested in the status of LLVM RISC V code generation, and Swift, Julia, and other such languages. And so LLVM provides a sort of common infrastructure, a common set of passes, analyses, optimizations, transformations in order to provide, to implement basically a whole suite of compilation-related tasks. So there's the LLVM and its code generator, but there's also a family of projects including linker, debugger, C++ runtime, so compiler RT, the equivalent of the low level of libgcc library, and a growing suite of projects as people upstream contribute new things, OpenMP implementations, SYCL coming from Intel soon. And so why are people interested in LLVM? Why interested in LLVM for RISC V? I think there are a number of reasons. I think first of all, we should make completely clear that GCC for RISC V is in fantastic shape. People have been using it to compile a whole bunch of things. So if you just want a working compiler, GCC is there. It's ready to go right now, well supported. There are a range of pre-compiled versions available, people upstreaming and increasingly cross-compiled tool chains upstreamed into distro repositories. But there are a number of people who prefer LLVM either for licensing reasons or because they rely on it as the backend for programming language. So Rust is perhaps the most notable example, and as I'm sure we'll be hearing later, it's becoming a dependency for any modern distro right now with librsvg and other libraries being ported. I think another LLVMs also have very good uptake in academia, research, and R&D. One of the reasons is that it's actually very easy to modify and add support for custom extensions. There's a very active developer community, and we could argue back and forth about GCC versus LLVM, but certainly there's a sort of a locus of interest around it for new and interesting compiler analyses and transformations. So I'm just going to give a little bit of a brief overview of what a Clang LLVM compilation flow looks like, which we'll sort of use to talk about the tasks that you take on when porting something like LLVM to a new to support a new architecture. So you of course have your C input. So in the case of LLVMClang, you put this through your C front end, and when porting it to an architecture, to be honest, there's very little you need to do to the Clang front end. You need to add support for the set of command line options which get passed through to the back end. Teach it a little bit about the target architecture so it can provide appropriate diagnostics, but beyond that it's order of a few hundred lines. So we have our C input. This gets eventually we get through to, this gets passed, we get the Clang AST, and that will eventually spit out LLVMIR, which probably most of you have seen in some form at least once. So this is so unlike GCC, this is exposed to the end user or the people who want to feed it in as input to LLVM, so people can actually pass that using other tools if you wanted to do your own stuff with it. Though in practice, most people implement their own extensions to LLVM using the library-based extension mechanism. So as you see, we've sort of lowered the C types in a fairly trivial way. int32t becomes LLVM's IR type I32, and LLVM IR has its own set of instructions and semantics. And one sort of common misconception is that it's some sort of universal IR in the sense that WebAssembly or other projects are trying to be. So once you've got to LLVM IR, you've actually already made a number of target-specific assumptions, which you need to do in order to sort of meet the CABI and maintain the semantics for your input. So once we have the LLVM IR, the next step from that is then putting that through the compiler middle end, and eventually this goes through a sort of a process which spits out what's called a selection DAG. And we're not going to go into details of that because it's not particularly relevant to what I'm talking about today. But the point is, everything that's going on the LLVM IR level, that's mostly sort of target independent and shared. So it's all the same code for ARM, AArch64, x86, Power, and so on. Whereas once you get to this step, you've done all of your target independent transformations and analyses. This is where the sort of porting effort comes in. So you're able to make use of a whole set of libraries and helper functions, but the task is essentially to take this selection DAG and to lower it to our final form, which is the outputted assembly or ELF object. So in this case, it's all fairly trivial because ultimately we have a single IR instruction, the add, which gets lowered to a little bit of extra junk in order to handle the function arguments from return, as well as the main meat of it, this selection DAG add node, which is trivially then lowered to the add instruction. So that's given a bit of a sort of high-level overview of the sort of things that you would take on while porting something like LLVM. So this includes, so LLVM for a number of years now includes an integrated assembler. So that's a relatively straightforward task of just supporting the RISC V assembler, the syntax. We start looking at defining So you've implemented your assembler, and that's actually where I started with the RISC V LLVM ports, as to provide a sort of base, a sort of solid base on which to build everything on top of. The next task you'll want to take on is doing something like defining the instructions. So what is which instructions does the architecture support and how are they encoded? So I'll just show a slightly verbose example over the next few slides, but you don't need to sort of study the whole thing. And I'll sort of step through the rest of these with examples actually. So this is the exploded definition of a single instruction in LLVM, and of course you don't need to write this when defining your new target. This is using its domain-specific language called TableGen. So this is specifying that we have up here. So we have a RISC V instruction and add. The assembler syntax looks like this at the bottom, and we have a whole bunch of encoding. So actually I've highlighted on the next slide, these are the lines that are relevant to encoding the instruction for target architecture, and these are the lines which are relevant for the assembly parser, which is actually mostly generated for you, and for specifying the inputs and outputs of the instruction. But of course, this is verbose, painful. If you had to write that for every instruction, it would become rather tiresome and not particularly easy to maintain. So it's you start adding in sort of classes which are a feature of the TableGen DSL, which mean that ultimately you can specify instructions using a fairly straightforward form such as this, which defines all of the register-register instructions in the base RISC V ISA. So that's enough in order to, provided that you have enough support code around it, that's enough to generate your parser, the assembly parser, and to actually produce object code from that. But we also want to handle the more common case, which is when you have LLVMIR input from Clang, Rust, Julia, or whatever else, and you want to work out how to convert that to RISC V instructions. And so that involves both writing C++ logic for more complicated cases, but in a simple case, such as an add, you just write these patterns. So these are just these are patterns on nodes of a selection DAG. So it's just a directed acyclic graph specifying that if you have an add node which looks like this, convert it to a RISC V instruction which looks like this. And I mean, from a high level, that's basically what it involves: going through each of the instructions, supporting that, implementing patterns in this way, and then most of the fiddly work is kind of around the edges. It's ensuring that the stack frames are set up properly, that the ABI is maintained, that various corner cases come up which are handled properly. Of course, with RISC V, we have it isn't just a single target, and although over time other architectures have also gained a whole range of different features and different options, I think RISC V is they don't tend to be exercised simultaneously. So essentially we have three base ISA definitions, so RV32I, RV32E, which is when you have only 16 registers, or RV64I. But then you have the question of, do you support the multiply, atomics, single precision floating point, double precision floating point, the compressed extension, and that's all fine. That's fairly straightforward. It's quite, every architecture, x86 adds new extensions with every Intel chip released. But there's also a whole range of ABIs attached to that. So whether it's which is specified in terms of XLEN, so whether it's RV32 or RV64, and then indicating whether, so just ILP32 would mean that it is essentially the soft float ABI. ILP32F is single precision, hard float for single precision, which means that your floating point arguments are passed via registers. And similarly for ILP32D and LP64D and so on. And the way that the RISC V ABIs are defined, it's actually pretty easy to handle these with a single function which is parameterized by the supported floating point length and the supported and the general purpose register length. But in terms of testing, you can see that there's once you start multiplying all these options, there's quite a lot to cover there. And there's more to come as people are introducing new custom and standard extensions and introducing new custom or standard ABIs. So the port of RISC V LLVM, back in the early days of RISC V, just when it was making its way out of Berkeley, there was a GCC port, which some of the Berkeley students had developed, and there was an initial LLVM port. And ultimately, I actually went and waited around a bit to see what was happening. I'd previously been working on a LLVM port for a research architecture at Cambridge, a large number of very simple in-order cores, but with its own ISA. So I kind of got quite up to speed on LLVM backend development through that. And I think we found that the initial RISC V LLVM port, although people managed to do some useful things with it, it was quite some way away from being ready for being committed upstream. So I sort of started a fresh effort trying to work in a very step-by-step taking a very step-by-step methodical approach, ensuring that everything was well tested, unit tested, and to the extent that I was able to, documented. And I guess over the past 18 months or so, I've been able to get a bit of funding, which has helped to sort of increase the time I can spend on this. I'll say more about status a little bit later, but there's now, this started as a downstream project, but with the intent of getting it upstream very quickly. LLVM has a pre-commit review policy, which in the early days, it took quite a while to actually get things up there. But that's sort of sped up substantially now that there are more people interested. I'm the upstream code owner, so that's things got much easier in that respect. And so, so at this point, there are, I guess, the sort of high-level view of the current status is that it's not there yet for hard float on Linux targets, but I'm targeting the next LLVM release of that. But there are, I know, multiple companies who are using it internally for their firmware builds on their embedded 32-bit targets quite successfully, occasionally working around various limitations, but finding it's doing what they need. So I think I've covered that. So in RISC V, as you might know, there's a compressed extension, and how that works is, so in the standard RISC V instructions, the RV32i, RV64i, every instruction is 32 bits. If you support the compressed extension, then for a subset of those instructions, you're actually able to encode them and encode them in just 16 bits. So this is not dissimilar to FOM2 or various other compressed instruction set designs, except that you're able to freely intermix them. And we actually had a fair bit of discussion about how to handle this in the compiler. There are a number of design choices that were considered. And one of the questions we had to answer quite early on was whether the instruction selector would be aware of a compressed instruction set. Because of course, if you have a 16-bit instruction for an add, it doesn't have the same. It has various restrictions on it, such as you have to have there's a restricted subset of registers that you're able to access. There's a restricted immediate field. And so there's one approach would be to try and teach the instruction selector about all of these instructions and have that produce it. We actually ended up doing something very similar to what GCC and the GNU assembler does, which is to actually handle it basically exclusively as a very, very late stage conversion. So you go all the way through register allocation, through the instruction selector, through register allocation, actually generate the in-memory representation of the machine instructions, and then we put it through a converter, which just is basically a table-based system that looks and sees and says, for this add instruction, can I convert it to a compressed add instruction? For this load instruction, can I do the same? And the advantage of this is that it quite substantially simplifies the logic throughout the rest of the back end, because I mentioned that we have those long lists of instruction patterns, and that's pretty straightforward. But there's a whole bunch of other target-specific analyses, such as looking at analyzing control flow and branching, and it becomes somewhat tedious if you have to ensure that all of that recognizes both the uncompressed form and the compressed form. And of course, it's an area where you can start to introduce errors. But I think that's the starting point rather than the end point. So we have it so that, and it's not completely naive in that the register allocator is aware of the fact that some registers are able to be accessed from compressed instructions, and so they would be chosen in preference to registers which can never be accessed from the compressed instructions. And I've gone a bit around in terms of how much to go into detail on the RISC V memory model support, so I'll try and keep it somewhat accessible. It turned out to actually be a larger body of work than I was anticipating. So as you may know, if you've been following RISC V over the past few years, one of the early and probably most successful standardization efforts in the RISC V Foundation was coming to conclusion on what the RISC V memory model should be. So the initial specification, it had various things to say about the memory model. Then some researchers at Princeton and others, they sort of pointed out that actually, like most memory models for most architectures, there were various things which were somewhat questionable. And they quite successfully managed to get a whole group of academics, practitioners and industry together and come to an agreement on the memory model, which ended up being a sort of very relaxed memory model, not dissimilar to AArch64. And so what do you need to do to support that in the compiler? And it's actually, the basics of it is relatively straightforward, because that I have with the C11 and C++11 memory model, there are a number of primitives such as atomic add, atomic subtract, atomic load, each with different memory orderings specified by the programmer. And all I really need to do is understand each of those. So this has been this is a compare and exchange, which has been that would have been lowered from the C++11 atomic compare and exchange, and then I simply have to convert that to whatever the memory model people tell me is correct, and then in theory you're done. But it's actually a little bit more fiddly than that. So in RISC V supports, it has two sets of atomic instructions. So you have the AMOs, the atomic memory operations, so atomic fetch, atomic add, atomic subtract, atomic OR, atomic XOR, and that's relatively straightforward to support. But then there's some more general instructions, so load reserved and store conditional. So if you want to do something a little bit more complicated than just load a value, add it, and atomically write that back again, then you rely on these primitives. So load reserved reads a value and it sets a reservation, and the granularity of that reservation is a kind of architectural, is dependent on the microarchitecture. But let's say it reserves that cache line, and then you do some computation based on that, and then later you do a store conditional. And if somebody else wrote to that cache line in the meantime, then your store conditional will fail, and then your program code, if it wants to be correct, should then loop back and try again and keep trying. And it's this looping again and keeping trying which can be problematic, because you want to ensure that this loop will actually terminate at some point. And so the RISC V ISA manual specifies various restrictions on what code can be placed between the load reserved and the store conditional in order to ensure what it calls the architectural forward progress guarantee. And the restrictions are pretty simple. It just means that you can't have the main thing you can't have are spills or loads or stores from main memory, or jumps or floating point instructions and that sort of thing. But the difficulty is that the compiler doesn't actually have an easy way of reasoning about that, or reasoning about the fact that, say, for this IR construct, once I start to decompose it to RISC V instructions, but before it's done various other analyses of transformations, it's not actually possible to specify that this region should be left alone and there shouldn't be any spills and that sort of thing. So it's actually a problem which other architectures face, and ended up sort of implementing a whole set of different hooks for atomic lowering, which currently RISC V is the only user of, but I'm hoping that AArch64 and ARM will move over. And essentially the approach is to lower to basically treat something like compare exchange as a black box when you lower it. So we see this compare exchange, we lower to we load something which is a little bit still very abstracted. So it's basically we know it's a RISC V compare exchange, but it's not converted to RISC V instructions until a very, very late stage, after all the other register allocations have been taken place and things like that, which ensures that there's absolutely no way that unexpected spills to the stack and that sort of thing are introduced. And although in practice, say, the other backends have managed to avoid this by having a slightly different code path for when you have a for when you're targeting O0, there's it's still a sort of theoretical concern, but I think it's worth addressing. Oh, I'll get to that. So in terms of testing and fuzzing, there's been I guess there's a few approaches we take. So most of it has been done through unit testing. So targeted tests written against the LLVM has a whole infrastructure for this based on giving input IR and then writing effectively regular expressions on the output to ensure that the assembly that you expected came out the other end. There's been an increasing effort to start to test with, of course, real-world programs. Multiple people are compiling spec with Clang and RISC V. And there's some great work last year from some interns at Qualcomm on fuzzing, and this was targeted on the assembly parser, so specifying a grammar for RISC V instructions, then trying to generate a whole bunch of different inputs and seeing how it differs between GCC and the LLVM assembler. So that was using, there's some related work for doing something similar with C. So that was inspired by, I think there's work some Google's done on so you specify, use sort of protobufs to specify your grammar, and then using LLVM's fuzzing library, you're able to instantiate that with legal and illegal values. So another challenge on the compiler side, or I guess another task, is supporting linker relaxation. So LLVM has fairly small immediate sizes. So if you have access to and of course it has fixed instruction lengths, unlike x86. So with x86, if you want to access global, you can stick the whole address there if you wanted to. Whereas with RISC V, you'd lower it to say a couple of instructions, so say loading the upper 20 bits, and then say loading with a 12-bit offset. But linker relaxation is when you allow the linker to look at all of these instruction pairs and then decide and find those cases where actually you didn't need the upper 20 bits because it is within range of the 12 bits offset, and then delete the original, the first instruction. And this is, and if you'd use that approach, you have to ensure that the linker knows, that the linker has access to every fix-up or relocation in the program, which effectively means every access to a symbol, because all the instructions could be moved or changed. Yes. Okay. Right, and I think so. Supporting RISC V's APIs, I mentioned, one of the challenges is that there are a lot of them. The helpful thing is that they're actually basically all very similar, in that they are fairly simple parameterizations of the supported floating point register length and the general purpose register length. So LLVM is actually structured so that a lot of responsibility for supporting the API is done in the front end. So this is something I've been talking to some of the people who've been porting Rust about, as they're also kind of have the responsibility of capturing cases where you need to. So effectively, it's a problem of, say I have a function which takes a unsigned integer and a signed integer. How do I convert that to LLVMIR, which maintains those semantics? And that's mostly done for us in Clang, but this is work which also has to be repeated for Julia, for Swift, and Rust and other languages. So one thing I did with this was I've implemented a Python library which aims to be I've got the RISC V calling convention. Initially, I called it the calling convention golden model. It's now called ABI cop. So this is a sort of tool which helps to test that the ABI is conformant to at least my interpretation of the RISC V ABI specifications. There's more work to be done there in terms of randomized testing. So it does has a fairly naive approach of doing randomized instantiations of function pairs, and then you can take your caller, compile that with GCC, take your callee, compile that with Clang, and hopefully you get the result you expect. But there's definitely more that can be done there. So moving on to status and where we're at, I think the first thing I'd like to highlight is that this started out as a project where I was the primary author, and It's expanded over time now, so we're at a point where we have multiple external contributors. I'm very grateful to contributions from companies like Qualcomm, Embicosm, Andes Tech, and others who've added support for features like are working on the compressed instruction sets, more recently TLS from Embicosm, and a whole series of assembler fixes and other things from Andes Tech. And I think we're starting to see, as the LLVM backend nears the point where you're able to do things like compile Linux kernel and Linux user space, there's a growing number of people who are interested in starting to contribute upstream. It's also been something I've tried to encourage through giving tutorials and that sort of thing. So I'll give a link at the end of the talk. I gave a tutorial at the LLVM dev meeting at the end of last year, which gives a sort of a introduction to hacking on LLVM and hacking on the RISC V backend in particular. So where we're at with LLVM, as I mentioned, there are multiple companies who are using it internally for their 32-bit firmware builds, but there are still a few limitations. So the TLS support is kind of in the review queue and will hopefully soon be upstreamed. So that's Fred local storage. Things like position-independent code remains to be implemented and upstreamed, and so the hard float ABIs, which are the ABIs that you want to use on Linux, aren't implemented yet. So a main blocker for that had been the 64-bit floating point code gen, but that was actually merged in the last few days. So imminently now be pushing forward on the hard float ABI support, which people want to compile modern Linux applications. There is a Rust port and an active community around that, targeting the baseline RV32i, so the RV32IM, I guess, whatever extensions you want to add to it. So that's, and then now that all the 64-bit stuff that they need is upstream, they're now looking at porting that to 64-bit as well. LLD, I should have mentioned also, that's another thing which I have other contributors to thank for. So Andes Tech did some work on adding support to RISC V to the LLVM linker, and it's there, it works. It's somewhat early days, so it doesn't support some of the features that I mentioned, like linker relaxation yet. That requires a bit more design work, but all the basic relocations are supported, and you can use it if you want to, but you can just use the GNU linker. So we'll be moving forwards with work on the hard float ABIs. That's probably priority number one right now. Other work which has been going on is on the RISC V vector extension. So I won't go into much detail about this. This has basically been led by Robin Krupp, who's a student at TU Darmstadt. If you've been following the RISC V vector extension discussions, it's an interesting compiler target, like ARM's ARM's SVE vector instruction set. One of the basic design decisions is that your vectors are a compile time unknown length, which is dependent on the microarchitecture, and so there's quite a few interesting challenges about how to support that. And there's been actually work from Robin and some of the other people working on vectorization LLVM, working on how to support that for RISC V, SVE, and other vector architectures which take a similar approach. Now, I think there's a talk later which will be looking at comparing code size on RISC V versus other architectures, just comparing RISC V, LLVMClang versus GCC. There's more that can be done to improve code compression, first to meet GCC and then hopefully to move beyond that. So I mentioned that that targeting the compressed instruction set is there's very little interaction with the instruction selection stage. So it's not quite unaware of the fact that you're generating compressed instructions, but there's still not much of a feedback loop there, and there's definitely more you can do. So specifically, teaching the register allocator about the compressibility of instructions, there's potential for benefit there. So let's say that I have a series of instructions, all of which use the same virtual register. So I know that that they want to use the same value, but it hasn't yet gone through the register allocator. If the register allocator is able to dynamically weight the choice of the registers, it can make a more sensible choice. Because if you know that one of the instructions could never be compressed anyway, then there's not much point in using one of the registers which is compressible. You'd be better off saving that for a case where you can actually improve code size. There's also, one thing we've noticed comparing GCC and Clang is that Clang's reordering of basic blocks can be quite aggressive. So what it's trying to do is to ensure that based on either profile data or static estimations, ensure that the common case or the hot path is sort of linear in memory, which is great for for cache effects and performance and so on. But if you're trying to minimize code size, that's not always what you want, because it means that your branch offsets tend to be larger, and so you tend to end up not being able to compress all your branches. And so tweaking this or adding ways of opting out that behavior is something to be further explored. So I'm particularly interested in talking to anybody who's been working on different language front ends for LLVM. So I've had, there is a Haskell LLVM backend as well, so I know they did a little bit of initial work, but I don't think there's been much activity there. So I think Rust has been most active. I haven't actually heard anything from the Julia or Swift community, but if you know people in that community who are interested, then please put them in touch. It would also be good actually to work together more on the ABI lowering and validation around that. So as you know, RISC V has a sort of set of standard instruction set extensions which are defined right now, but there's also an ambition to extend that set. The RISC V vector extension was one example of this. There's also active work on defining new instructions for bit manipulation. And so I'm quite keen to work with that working group to provide support for the compiler before it's actually standardized, in order to provide feedback in terms of how difficult it is to support compilation to that extension, and how getting statistics on how often you can actually select these instructions. So that'll hopefully be something we move forward on in the next couple of months. I've suggested that it would be worth for the proposed extension if they could just pick an encoding, even if it's not final, so at least those of us who are doing those sorts of experiments can sort of cross-check our tooling to ensure that the assembler's working the same way and that sort of thing. And there's more stuff coming in terms of RISC V standards. There's been talk about supporting floating point registers supporting floating point instructions on values held in general purpose registers. New ABIs for embedded targets, so ABIs where long double isn't a 128-bit float, and other changes. And so this will of course lead to continuing work in the future. And there's more to do in terms of support for target-independent LLVM features that we benefit from. So I mentioned code size, and the machine outliner is a very promising feature that's been pursued more recently with AArch64. So effectively, this is the opposite to inlining. So with inlining, you see that a function is used and that you don't actually need to have the external function call. You can copy it into your function. With outlining, you look and you find common code sequences, and because you're trying to optimize code size, you decide, well, actually, I could pull this code sequence out to a separate function, and it would be less expensive in code size to just have a call to it. And so it's obviously not positive for performance, but useful for people who are really trying to cram their code into a small amount of space. And we're actively working on further testing on more real-world applications. I guess in the last couple of months, it's mostly been people who are using it on their own code bases, and they've been feeding back upstream when things work or they don't. We're moving towards taking a more structured approach to I guess proactively testing on real-world programs and benchmarks. And on the 32-bit side, Zephyr, FreeRTOS, and moving towards Linux and FreeBSD on the 64-bit side. and I guess a more automated comparison to other tool chains and I guess other targets as well in terms of code size, like comparing RISC V versus ARM. So I guess I'm getting towards the end of the talk, but that is roughly the end of it. I should say that Low Risk is hiring. We have about 5 positions open. We're sort of ramping up a lot more work in order to deliver free and open source hardware and software. So if you're interested, have a look and talk to me or Luis or Philip afterwards. If you want to get started hacking on LLVM, I put together this tutorial at the LLVM dev meeting last year, which a lot of people found helpful. If you have problems with it, let me know. And at that point, I'll see if there are any questions. Thank you.
So, if I remember correctly, well, from a couple of years ago when it was hacking LLVM, the IR is not completely machine independent, right?
Correct. Yeah.
So if
Yes,
I want
Alex, can you repeat the question?
Oh, yes.
Yeah.
Thank you for that. Yeah. So the question was that. Sorry, actually, move on to the question, and then I'll repeat the whole thing.
There's not
Yeah.
hard to it. Maybe I can stand up and speak a bit louder. So the LLVM IR is not completely machine independent. And so if I'm going to write a front end for LLVM, for a different language, how much work do I have to put into supporting all the different variants of RISC V, especially 32 and 64-bit variants?
Yep. Okay, so the question was, given that LLVM IR isn't actually fully target independent, how much work is there in order to support a new front end in order to support the ABI? So it's something that we talked about in the LLVM community back and forth for a while, because that it seems unpleasant that people need to do this for each new front end language and potentially get it wrong. So what you basically need, so it depends on the ABI that you're targeting. So in the case of RISC V, you actually do need to understand for your given your function signature, you actually do need to go through and count the registers and determine whether this value is going to be passed on the stack or not, because it affects whether you need to add the sign extension or zero extension annotations and things like that. So there is, I mean, it's hard to quantify how much work there is in that. I guess writing something not that hard, testing it and ensuring that it works, more work, and I hope that's an area where more of us who are working on that can collaborate, because the testing problem is basically the same. One approach is the approach I mentioned of doing separate compilation and compiling the caller and callee under different compilers, or perhaps extending the ABI cop tool so that it does a very simple form of code generation in order to provide, I suppose, more of a even more of a golden model. Right now it just spits out a sort of text description of what you're expecting. But I'd be interested in talking more with anybody looking at doing that.
Great. So you have 2 minutes, 1 minute now.
Anyone else?
You said people are using Clang, or at least LLVM, to compile their firmware. Do you know why they're doing that over OpenCC? Is that because of Rust?
So typically they've standardized on LLVM and Clang for whatever reason throughout the company. They have toolchain teams who will support that, and so it mostly stems from that. Excellent. Thank you very much.